You flip a switch, a light comes on. Simple, right? But what's actually going on inside that wire? I mean, really happening at a level you can't see. Well, today we're going to pull back the curtain on one of the most fundamental forces that powers, well, everything. We're talking about electric current. Let's dive in.
So here's our game plan. First up, we're going to nail down what electric current actually is. Then we'll get into the formulas, the real tools you need to measure it. We'll even take a quick peek at electrical power. And then, you guessed it, it's time to put it all into practice. By the time we're done, you're going to look at a simple circuit in a completely new way. Okay, let's get right into it. Section 1. To really understand the flow of current, you first have to ask, what is it that's even flowing? And that, my friends, brings us to the absolute star of the show, electric charge. So what in the world is electric charge? You know, it's a fundamental property of matter, just like mass. It's just there. We measure it in a unit called coulombs. And here's the crazy part. A single coulomb is a massive amount of charge. We're talking about a mind-boggling number of electrons. A single electron's charge is just a tiny, tiny fraction of 1 coulomb.
Okay, so you've got all this charge. What happens when it decides to get up and go somewhere? Well, that is electric current. It's not the charge itself, it's the rate of the flow. How much charge is passing a point in a certain amount of time. We measure this flow in amps. You've probably heard them called amps. And it's pretty simple. 1 amp just means that 1 coulomb of charge is whizzing by a point every single second.
Now here's a really cool, kind of weird piece of history that we're still dealing with today. Back in the day, scientists like Ben Franklin guessed that electricity was a flow of positive charges. So they drew all their diagrams with the current flowing from the positive side to the negative. We call that conventional current. Turns out, they had it backwards. It's actually the negative electrons flowing the other way, from negative to positive. But to avoid confusion, we all just stick with the old way for our diagrams. It's a convention, but it's super important to know what's really happening under the hood. All right, concept down. Now for the fun part. Let's turn this idea of flow into something we can actually calculate. And you're going to love this. The formula is beautifully simple. And there it is, I equals Q over T. This is the heart of it. It just means that the current, which we call I, is the amount of charge, Q, that flows past a point, divided by the amount of time, T, it took. That's it. So simple, but so incredibly powerful. Let's make sure we've got these variables straight. I stands for current, and we measure that in amperes, or A. Q is our charge, measured in coulombs, C. And T is time, and this is crucial. It has to be in seconds. You know, in physics, getting the units right is half the battle, so this little table is your best friend. So let's picture this inside a real copper wire. In metals, some of the electrons, the little outer ones, are kind of like free agents. They're not tied to any single atom. They can just roam around. Now, when you apply voltage, that electrical push, they all get nudged in the same direction. It's not a race. It's more like a slow collective drift. And that massive coordinated shuffle of electrons, that is the electric current. Okay, time for a quick example. Let's say 10 coulombs of charge flow past a point, and it takes 2 seconds. What's the current? Well, we just grab our formula, I equals Q over T. We plug in the numbers, 10 coulombs for Q, 2 seconds for T. 10 divided by 2 is 5. So the current is 5 amperes. See? Simple. So, we can measure current. Great. But what makes it flow in the first place? And what tries to stop it? Answering those 2 questions leads us to one of the most important, most famous laws in all of physics, Ohm's law. Before we get to the law itself, we need to meet 2 new characters in our story. First up is voltage. The best way to think about voltage is like electrical pressure. It's the push that makes the current go. The more voltage, the more push. And then there's resistance. Resistance is exactly what it sounds like. It resists the flow. It's like a narrow pipe or a kink in a hose. It makes it harder for the current to get through. And we measure that in ohms. And here's how they all relate in Ohm's famous law, V equals I times R. Voltage equals current times resistance. This little equation is the absolute cornerstone of circuit analysis. It shows this beautiful relationship. If you keep the resistance the same and you increase the push, the voltage, you're going to get more flow, more current. Makes perfect sense, right? So let's just hammer this home. V is for voltage in volts. I is for current in amperes. R is for resistance in ohms. VIR. Remember those 3. They're the foundation for pretty much everything else. All right, let's try another one, this time with Ohm's law. Imagine you have a 12-volt battery hooked up to a resistor that has 4 ohms of resistance. How much current is flowing? Well, we take V equals I times R, and we just need to rearrange it a bit to solve for I. So current equals voltage divided by resistance. We plug in our numbers, 12 volts divided by 4 ohms, and we get 3 amperes. Boom.
Okay, so we've got the push, voltage, and the flow, current. Knowing those two opens the door to another really important idea, electric power.
So what is power? Simply put, it's how fast work is being done or energy is being used. You know, when you buy a 60-watt light bulb, that watt number is telling you exactly how quickly that bulb is turning electrical energy into light and heat. It's all about the rate of energy transfer. And you'll love this. The formula for power is maybe the easiest one yet. It's just P equals V times I. Power equals the push times the flow. Voltage times current. That's it. It's a great little formula because if you know any two of those, you can always figure out the third one. All right, we've gone through the ideas, we've looked at the formulas. Now it's time to put that new knowledge to the test. Let's do a few quick practice problems to make sure all this stuff really sticks. First one up. Imagine 20 coulombs of charge flow through a wire, and it takes 5 seconds. What's the current? Go ahead, think about it. Which formula do we need? Yep, our first one, I equals Q over T. So we take our 20 coulombs, divide by our 5 seconds, and what do you get? 4 amperes. Exactly right. Okay, problem number 2. You've got a circuit with a 9-volt battery, and you measure a current of 3 amps. So what's the resistance? This one calls for Ohm's law, right? We need to rearrange it to find R. So R equals V divided by I. We plug in 9 volts for V, 3 amps for I. 9 divided by 3 is 3 ohms. You're getting the hang of this. All right, last one for today. Let's say you have a gadget that's plugged into a 10-volt source, and it's drawing 2 amps of current. The question is, how much power is it using? Remember that super simple formula. Power equals voltage times current. So 10 volts times 2 amps gives us 20 watts. Perfect. You've got it. And honestly, that's the big takeaway. Think about it. With just a couple of very simple ideas and 3 formulas, you now have the tools to calculate the most fundamental properties of a simple circuit. The push, the flow, the resistance, even how fast it's using energy. That is an incredibly powerful toolkit to have. But here's the thing. We've only been looking at circuits with one single simple path. Real-world electronics are almost never that easy. So what happens when the path splits into 2 or 3, when you have complex loops and branches? Where does all the current go then? Well, that's a much bigger puzzle, and it's exactly what we'll be tackling next time. Thanks for joining me.